Hello, everybody. Yeah, I'm going to talk about how we use lab data. And I'm going to really take this back to basics because a lot of the time there's things that people think they know and there's language issues. So I'm really going to break this down so that everybody understands the relationship between lab data and what we see from observations. With a little bit of motivation, we've already heard a lot of talks and a lot of them have had dust. We know that there's dust in just about everywhere, whether it's dying stars or stars being born or in between stars. And we also have dust out beyond our own galaxy. In fact, we see dust even as far back as we can go at high redshift. So dust, to understand dust is really important, but there's a lot of basics that often get overlooked when we're trying to model these things. So I'm going to break this down, and I'm going to start with, how do we actually do these observations? So here I have a star and it's emitting some light. And if there's nothing between us and the star, we just get starlight. But if there's something between us and the star, now the starlight is going to be absorbed. It might be re-emitted. Some might get through unscathed. Some is going to be scattered. And we need to understand what that cloud is. Now, that cloud could be close to the star. It could be far away. It could be very large geometrically, very small. And I'm going to get into how that then relates to what we look at in the lab. Just to kind of motivate some of this, we've seen some models where people have used silicates or amorphous carbon or whatever. I just want people to understand how important it is to have proper lab data. So here I have two particular materials that are just made of carbon. They are both made of carbon, but how they interact with light is completely different. And that has a knock-on effect. You can imagine radiation pressure on graphite is going to have a bigger effect than radiation pressure on diamonds. So it's really important to understand all of what goes into extracting optical properties from our dust species. It gets worse than that. Here I have rubies and sapphires. Most people don't know that this is actually the same mineral. They are both corundum, aluminium oxide. And what gives them the different colors is the impurities within the crystal structures. So even impurities affect how light interacts with matter. And so we really need to know the crystal structure, we need to know grain sizes, we need to know all sorts of things in order to really nail this down. We've heard a lot about silicates. This is a scary looking graph, just to kind of bring this together. All silicates are made of these silica tetrahedra. There's a silicon in the middle of this pyramid with an oxygen on each apex. It can share an oxygen, so you can put them into all sorts of different configurations. So here I've got two stuck together. This one is a chain of those pyramids. This one is two chains stuck together. You can build this up, and in fact, quartz, which most people know what quartz looks like, that's actually where you've got a full 3D structure where every oxygen is connected to another pyramid. What again I want to point out here is that as you change the crystal structure, and in fact as you change the cations that charge balance these units, as you change the impurities, you get very different interactions with light. And so this is the stuff that we can use to diagnose what's out there. Okay, so apparently my internet connection is unstable, so bear with me. So again, I said I was going to come back to basics. So we all know you've got light. You guys can see me because light is reflecting off me and then being transmitted through the ether, but that's a whole other thing. So we have reflection, we have propagation through a material, and then we have transmission, how it gets out the other side. So I've got some light hitting a slab of material. Some of it will be reflected, some of it will go on through. If it goes through, it's also going to be reflected at the other boundary, and some of it will get out the other side. Okay. This is just the basic setup. This is true whether we're talking about a huge cloud of dust out in space or whether we're talking about a pane of glass, right? This is what we're looking at. So what's actually happening as the light goes through there? Well, the light can bend. That's the stuff that we usually learn even in high school. It can be absorbed and re-emitted. I really like this word luminescence rather than emission. It's such a lovely word. And it can be scattered if there are places where it can reflect off of things. So you've got different phenomena that are going on. If you've got a nice smooth slab of glass, you're getting very little absorption and you're not getting much scattering. But if you've got something like a big cloud of dust, you've got all of this stuff going on. Okay, I want to just take a step back and talk about the language that we use when we talk about modeling dust and the danger of using the letter K. First of all, some of this is bound up with, we already have a problem that in science, the word theory has a very distinct meaning that is different than how it's used in the English language generally, right? You have the same sort of problem with opacity. Opacity just means opaqueness, and that is something that can be used in general language. It has a very specific definition here, and opacity is actually the same as mass absorption coefficient. There's also a thing called absorbance, and I'll show you that that's equivalent to optical depth. And then we have the letter K, Boltzmann constant, and also opacity, and also the mass absorption coefficient, and also some other things as well. And so I really wish that we could come up with some other letters or symbols or something. But this is where I think it's really easy to make mistakes on, oh, that's what this K is. And I'll come back to this theme as we go on through. So let's talk about opacity. And now I'm talking about the scientific definition of opacity. So here I have my slab of material. And again, this could be a slab of glass. It could be a slab of something else. It could be our dust cloud. We've got incident radiation on that. The cloud or slab has a density rho and a thickness dx. And what comes out the other side, what is transmitted, is f prime of lambda, okay? So we can define what the difference is. Just df is the difference between what goes in and what comes out. We know that the difference is going to be because of the opacity of the material, the density of the material, and how much light was hitting it, and how thick the slab is, okay? And now we can do some algebra and some calculus. Can you tell I have a teenager at home? And we end up with an equation that tells us, okay, if you have got a slab that is X thick and rho density and has material with an opacity K lambda, then this is what's going to happen as light passes through it. Nice and simple, okay? We define optical depth as being that exponent, that is, how is the light dropping off as it passes through this material? And we also have this term, which I've called kappa. I'll come back to that in a second. Kappa abs is usually called the absorption coefficient, but it's not the same as the mass absorption coefficient. But it's a combination of the opacity and the density, okay? These are all terms that you'll find in the literature as you're trying to get data to use in your models. So I'm trying to kind of pull the pieces out so you know what you're playing with. Okay, so I've just translated that into using this absorption coefficient instead of the opacity. Okay. So when we talk about what's happening inside the material, we have light is refracted, but also absorbed. We've just talked about that, but I want to talk about in terms of, we've got transmission and reflection. So instead of just having transmission is what's left over that's not reflected, now we have to have an absorption term. So here's my slab of material. I've got some light hitting it, some light is reflected, some light goes through, and what's transmitted is still T of F, T is the flux of transmitted light relative to incident light. But now we've got an equation that basically says I have incident light that hits this, and then some light is reflected. Then some light goes through, but that's going to diminish according to the properties of the material, that's this kappa, and the thickness of the shell, that's this L, and so that's going to diminish the light. So that affects what's going to be transmitted, but so is the reflection here, and that's this term here. Now we're going to assume that the reflection at each boundary is the same. That makes it a little simpler. But now I've got an equation that relates transmitted light, reflected light, and the absorption. And so we can measure what's transmitted, put a detector here, what's reflected, and that way, and if we know how thick our sample is, we can get this absorption coefficient out. This is the best way to measure the optical properties, because you're not artificially losing light to reflection, or you're not artificially making assumptions about what's going on inside the material. And that's what I just said. So basically we can get out this extinction, this absorption coefficient, which also, if we know the thickness, we can get the, and the density, we can get the mass absorption coefficient. Confused yet? There are so many things that are called absorption coefficients, so I just wanted to go over them briefly, just as a reminder. So We have the absorption coefficient. That's what I'm calling kappa. It's sometimes called alpha, and it's sometimes called the volume absorption coefficient. We have absorbance, which is also sometimes called alpha, because yeah, let's use the same symbol for two different things. And that's basically equivalent to optical depth. So the optical depth of a piece of material is quoted as absorbance. That is often what is published, especially in material science and earth science, in terms of what the property is that is being plotted in graphs and given to you. We have this letter K, which is the imaginary part of the complex refractive index. I'm going to come back to that in a second, but that is sometimes also called the absorption coefficient. And then we have the mass absorption coefficient, which is not the same as the K above, and it's not the same as kappa. Again, I just want to pull all of this out because I think that there's often confusion when people are trying to extract what they need to compare with their models. Okay, and you will find that that word absorption will sometimes be replaced by extinction and sometimes by attenuation, depending on whether you're looking in, say, atmospheric science or material science or earth science. And all of these things are useful to us, but we need to know the language. Okay. All right, so bringing this together, I've got reflection. I have this term reflectivity, which is just the fraction of reflected light compared to instant light. Likewise with transmittance is actually the same as transmissivity. So if I just put these in here, but the reflectance and the absorbance are not the same. So here I've got absorbance is that power. It's basically the optical depth. So again, just to bring all of this together and make sure we're saying this, we can measure the reflected light. We can measure the transmitted light. We cannot directly measure absorption, but we can extract it by putting all of this together. Okay, so this is now my equation for I can measure R, I can measure T, and so I can get out A. And once I have A, I can then use that to compare to what I'm seeing in astronomical spectra. Now let's just digress briefly again and talk about the complex refractive index. So basically I'm taking the refractive index that we all know and turning it into a complex number. This is related to the dielectric function. It's the square root of the dielectric function, which is also a complex quantity. The n, the real part, is just what, that version of refraction that we learned in high school. That's the change in the speed of light. That's the real part of the refractive index. The imaginary part is the absorption. And I want to show what effect it has. And just as a reminder, this K is not the same as kappa and is not the same as opacity. Okay, so what effect does it have? So here I've got light written just as a simple sine wave. And I'm using zeta for my wave number because that's also a K and it's just getting way too confusing. So it's now zeta. And so once my light passes into a medium, it just changes the velocity of light. And so I put that into my wave equation. And so now I have the letter M here, and that's my complex number. So I'm going to put it out as its complex number, and then I can do some algebra and end up with an equation that looks like this. So now I've got still a wave. So now this is the wave going through the light, and then this is how the light is diminishing. So you can see here that the K is basically the decay constant. It's how the light is actually being absorbed. So that's why it's called the absorption coefficient, but it's part of the refractive index. Okay, and so here I've got, we know now that this here is this decay, and that is going to be 4 pi K over lambda, and so we can use that to extract it. So to extract the optical constants, remember this is our equation. We've got how the light changes as it goes through a slab of thickness X. We've got how the wave is behaving. So now with thickness X, we've got a decay of zeta K. And so we can basically take the zeta K, which is here, and put it into here. Remember that this is the amplitude, so I have to square it. So that's why it's 4 instead of 2. And I get out that my this kappa is related to K. And so now that means that if I can measure transmission, I can get kappa. And if I can get kappa, I can get K. And if I can get K, now I can get the optical constant. So I can measure T and I can measure R, as we saw before, and I can get kappa, and therefore the imaginary part of the complex refractive index. There's another way of doing this that's even better, which is to do transmission experiments on multiple thicknesses, because then the only difference is the R will basically disappear. The reflections will be the same, but you've got multiple thicknesses. So now you can get K out without even doing two different experiments. You can just do multiple thicknesses with transmission. And once we've got R from that, so we work out what K is. Once we've got K, we can plug it back in here to get the reflection. And once we've got the reflection, we've got a relationship between K and N, so we can back out the real part of the refractive index. The advantage of this is that it's all measured. It's not something that you're using Cramer's chronic analysis, which is the classic way to try and extract optical constants. This is all completely directly measured through transmission. Now, people will say, but my dust cloud, my cometary coma, my thing that I'm looking at is not a slab. No, it's not, but you want to do the slab experiment in the lab. And the reason why is that this is what's actually happening when you've got particles. And if you've got particles, you're going to get reflection off of them in different directions. And so what you measure as transmission is not clean. You're losing light. So you're actually going to overestimate the opacity, because light is not coming to your transmission detector, but it's also not being reflected back out to your reflection. So if you do it this way, it's a problem. Now, if you do it this way just to get a transmission and you're just comparing the transmission, that's fine. But if you're actually using this to extract optical constants, you're going to have the wrong numbers. Okay. And this kind of demonstrates that. This is from a paper by Mara et al. In Icarus in 2010. They used hematite. And this is the top is the real, that's N. The bottom is the imaginary, that's K. And what you've got here is what you get if you use their particulate sample, which would be like this, versus a bulk sample of the same material. And you can really see the difference. And so if you use this particulate optical constant to then calculate, oh, what does this particle distribution look like? What does this grain shape look like? You're not using the right constants. You really have to do a slab bulk experiment and then use that to calculate, or only use the transmission to compare directly. Don't use it to get optical constants out. So let's go back to our looking at dust in space. I want to now compare spectra. And so when I want to do that, basically we think about it in terms of the cross-section of the particles. We have an extinction that's made up of the scattering and the absorption. And we typically calculate this from the optical constants rather than comparing just to a transmission spectrum. And we usually come up with these Q factors or Q values, where this is the way in which the particle doesn't behave like a black body. It's how it deviates from a black body. But we can calculate this from the complex refractive index, and this is what most radiative transfer models do. You can also use the Q factors and directly compare with transmission spectra, but that is a little tricky because you might have shape effects you're not accounting for. So when we talk about, I've been talking about absorption, I just want to remind you that a lot of things we're looking at are emitting, but according to Kirchhoff's laws, emissivity equals absorptivity. So, you know, everything that we've just said, it works for using for absorption. So you can use that same Q value that you extract, or absorption value that you extract, and use it to calculate what the emission should be. And it's just the inverse, right? And so we've got our Q values in space. We've got our absorptivity values, which are therefore emissivity values, and we can see what's going on. So now we can calculate what the flux from a given grain is going to be. We've got how hot is it and how is it behaving not like a black body. Okay, so this is, we can get absorptivity, we can use that as Q, we can now calculate what we're getting from the dust. Obviously that's oversimplified, because what you're really looking at is the sum of all of these pieces, and some of them are going to be an absorption and some of them are going to be an emission, and there might be starlight in there as well, but you get the idea. This is why we do radiative transfer modeling, right? Okay, so again, let's talk about how Q relates to lab data. In the lab, we measure the absorptivity and the absorbance. And so what we have is that the absorbance is essentially the same as tau, and the absorptivity is the same as Q. So when you're looking at trying to use lab data, if you just want to compare to what you think your Q values are for a spectral feature, you can look at a transmission spectrum and it's going to be pretty close, especially in terms of the shape and peak position. If you're using mass absorption coefficient, that's actually equivalent to optical depth. So you need to be really careful with how you use that information. We can use the dielectric function or the complex refractive index, and we can calculate what things will look like. Now, most people are familiar with me theory. That's considered to be an exact technique. There are extensions of it. It's really hard to do an exact calculation for something that's non-spherical, but there are things that do it, like the discrete dipole approximation, like the T matrix. There are also other things we can use, like effective medium theory. But we saw earlier things like using grain size to get a different shape for a silicate feature in Young's disks, protoplanetary disks. What I want to point out here is, this is again from that Mara paper, this is magnetite. You can see here that if you use me theory versus using a continuous distribution of ellipsoids, you get quite a different shape of this feature. So you've got to be really careful about saying, oh, this shape that I'm seeing in my spectrum, it's because of grain size, it's because of grain shape, it's because of composition. It could be any of those. And so there needs to be a little bit of care taken when we say, oh, it's got to be this. I know I talk really fast. I had a lot to say. So in summary, beware of the letter K. It's evil. When you're looking for data to compare with your observations, it is the Q value is equivalent to absorption and transmission spectra, and the mass absorption coefficient is something else, and it's closer to optical depth. And whether we're talking about calculating from refractive indices or especially extracting refractive indices, there's a lot of data out there that is compromised by it being done on small grains rather than on bulk samples. And I'm going to leave you with a cartoon. Thank you.
Thank you very much for this nice talk. I will wait for, there are currently no question yet in the ISM Dash channel, and I also don't see any raised hands. So maybe while people are thinking of questions, could you maybe say something on the setup of the lab? Do you try to simulate some temperature conditions, or where do you get your samples?
Right, so that's a great question. So in fact, there's various different setups. We do actually measure from about 0.2 microns all the way out to about 200. But it's just like with our instruments for observing in space, that's 3 or 4 different instruments that you need to use. So we have one that's for the near UV to near IR. We've got one that's from the near IR to the mid, and then one for the far IR. And you're actually going to need to have samples of different thicknesses. So remember, it's a slab, but you want it to be transparent enough to have some light go through so you can measure it, but not so transparent that you don't get any absorption. So you have to get the thicknesses in the right range, and that's going to be different in the ultraviolet than it is in the infrared. So what you want is a sample that is big enough that you can basically slice it up into pieces. And so actually we've done a lot with amorphous, glassy silicates. In fact, most of them are made in a lab that studies lava, because most of the compositions that we care about, like pyroxene and olivine, are in fact the sort of things that form from lava. And so we make basically blobs of glass that's in different compositions, but we can make a big enough blob that we can then slice it up, and it is homogeneous and isotropic, so we have the same sample for all the different measurements. We don't do much with temperature, just because there's already a lot going on. And for the amorphous silicates, it's not going to make a huge difference because that feature is so broad. Where that really matters is if you're doing crystalline stuff out in the far infrared.
Okay, thank you. There's a question, don't bulk samples have their own issues, for example, particle-particle interaction rather than isolated particles?
So I think it depends on how you think about the sample. If you've got something that is agglomerated, so you've got something that's made of different particles, then you have exactly the same problem as you have with distributed isolated particles. Typically, the way that you do isolated particles is to embed them in a potassium bromide pellet, right? And then they're separated. But what we do is to have a sample where it is just that sample. And if it's glass, it has no boundaries. You're trying to make something where it really is the only reflections are going to be at the inner boundary and at the outer boundary, as it goes in, as it goes out. And as long as you don't have any cracks or anything like that, it shouldn't make any difference. It gets a little trickier when it's crystalline, but you should still have the same problem if it's a single crystal. If it's a combination of crystals, then yeah, you have that same problem of specular reflectance.
Okay. There's another question wondering if you use PAHs in your experiments and if you could speak about them.
So pHs are tricky, and this is where, people class pHs as dust, but they're not. They're molecules. And and so, I mean, they're in this weird zone of they're really, really big molecules. So are they more like dust? But they're much more difficult to play with. And so we really haven't done much with that. I'm more interested in replacing some of the optical constants that are out there. So for instance, most people use the graphite that is in Drain and Lee from 35 years ago. And there are problems with that, we've learned a lot about these things, and that, isn't what graphite would behave like. And so I'm not aware of a good set of graphite data. So I would like to produce things like that rather than pHs, where I think there are a lot of people producing different materials that you can use in models.
One last question. The dust emissivity index related to the mass absorption coefficient is known to vary in galaxies. Are there any lab experiments currently that could give insight into this?
Right. So this is actually an area that I think, for about 10 years now, and I haven't done these experiments, but I'm aware of the work, and we basically have done it a little bit, but not as widely and not with temperature effects. So you're going to have grain size effects, you're going to have temperature effects. There's also going to be crystal structure effects. There's work done in France by Karine Demick, where she was really focusing on this, mostly with application to Herschel. But this was really about looking at what happens to that, that long wavelength emissivity as you go to different places. I mean, even within carbon stars, if you look at the emissivity index of the SED for, say, IRC 10216, probably the best studied carbon star, it's a different emissivity to the Egg Nebula, which is ostensibly what IRC 10216 will become. And so there's going to be some evolutionary things go into there. So I think it's a really interesting area. I think it's really complicated to disentangle the pieces.